Imagine a user types this exact messy query into your search bar. What happens if someone lies to get money, right? They're looking for a specific legal statute, Section 420 IPC, that covers fraud. But what actually happens in most systems? They completely fail. It's wild. But this simple, everyday question immediately exposes just how brittle standard search architectures really are. Relying on just one search method basically leaves you stranded. A traditional keyword search, like BM25, misses the legal document entirely because the words lies, get, and money simply aren't in the formal statute. Zero shared vocabulary. But then, a modern dense or semantic search also misses it, unless the embedding model was explicitly trained on dense legal text to know that lying for money actually means Section 420. So, neither method works perfectly on its own. So how do we actually fix this? Well, welcome to today's Explainer, where we're completely demystifying the production-ready retrieval architecture that powers modern AI. Information retrieval is the absolute engine under every retrieval-augmented generation system, every single search bar, and every fuzzy document lookup. We're tearing down the academic theories and looking exclusively at the 2026 standard that actually works in production. Let's get into it. Here is our agenda for today. 1. The RAG search dilemma. 2. The 4-layer architecture. 3. Evaluating retrieval success. And 4. Hard-won production lessons. Section 1. The RAG search dilemma. Real search in the real world has to handle two wild extremes. Keyword search is super precise but totally brittle, while dense search casts this massive net but completely misses exact keywords. The crucial takeaway here, you literally cannot choose just one. The 2026 standard architecture isn't a single method at all. It's a chain of complementary methods. A hybrid approach is the absolute default now, where each step catches the failures of the one right before it. Everything else is just tuning. Section 2. The 4-layer architecture. All right, let's build this out. Here are the 4 key layers of the modern pipeline. Step 1, sparse retrieval. Step 2, dense retrieval. Step 3, fusion. And step 4, the cross-encoder re-rank. If you're building a search system, you're essentially picking the layers you need from the stack. So let's break down exactly what's happening in each of these steps. Okay, step 1, BM25. This is your sparse retrieval layer, basically your classic keyword search. It runs over an inverted index and is incredibly fast. We are talking sub 10 milliseconds per query on millions of documents. It absolutely nails things like statute references, product codes, and exact error messages. And fun fact, standard parameters, like K1 equaling 1.5 for term frequency saturation, rarely need tuning. The original defaults are usually exactly what you need. Moving on to step 2, dense retrieval. This is your vector search. It encodes the query and the documents independently into vectors to capture paraphrases and semantic similarity. It's a little bit slower, maybe 50 to 200 milliseconds per query, but it bridges the gap when users don't know the exact keywords. For most English semantic retrieval, you'll want to use a fast and strong bi-encoder model, like All-Mini-LM L6v2. If you need absolute top accuracy, you might look at something like BG large N v1.5. So now we have 2 sets of results, right? How do we combine them? That's step 3, fusion. Specifically, Reciprocal Rank Fusion, or RRF. RRF is the absolute easy default because it completely ignores raw scores, which is fantastic because your BM25 scores and your vector math live in totally different universes anyway. It just uses rank positions. You sum 1 over a constant k plus the rank, and that constant k is 60. It's the published default, and again, you almost never need to touch it. Finally, we finish the stack with step 4, the cross-encoder re-rank. The dense retrieval we just did in step 2 was a bi-encoder, meaning it encoded the query and document independently. A cross-encoder encodes them together, scoring each specific pair. This captures all that fine-grained relevance that the earlier layers missed. Now, yes, this process is computationally heavy and a bit slower, but you amortize that cost efficiently by only running it on the top 30 results from your fusion step, keeping just the top 5 for the final output. Pretty smart, right? Now, this is where it gets really interesting. Your infrastructure choice scales dramatically based entirely on your document count. If you have under 100K documents, you don't even need a separate database. Just run in-memory BM25 in your embedding model. Boom, done. As you scale up to 10 million documents, you'll need parallel systems like FACE or pgvector alongside Elasticsearch. At 10 million plus, you're looking at specialized vector databases like Qdrant or Milvus with built-in hybrid support. And at the absolute best quality frontier, you're deploying three-way search plus Colbert late interaction re-ranking. Section 3. Evaluating retrieval success. You absolutely must budget time for evaluation before you ever test your end-to-end AI accuracy. Here are your 3 major metrics. Recall at TAE asks a simple binary question. Out of all your queries, how often is the correct document sitting in the top K results? MRR, or mean reciprocal rank, looks at the average position of the very first relevant document. An NDCG at K is slightly more complex. It accounts for relevance gradations, rewarding the system more if the highly relevant documents appear higher up than partially relevant ones. But here is the absolutely crucial point. For Retrieval-Augmented Generation, recall at K is literally everything. It is the single most important number on your dashboard. Think about it for a second. If your retriever completely misses the passage that contains the answer, the language model simply cannot answer the user's question. A reader cannot fix what the retriever entirely missed. When things do fail, and let's be real, they definitely will, here is a fantastic debugging tip. For your failing queries, simply run a diff on the sparse and dense rankings. If the keyword search finds the right document, but the vector search misses it, you've got a semantic ambiguity. You might need better embeddings. If the dense search finds it, but the keyword search fails, you have a vocabulary mismatch, and you need to add the missing terminology. It's like a giant puzzle. Section 4. Hard-won production lessons. 80%. I really want that number to sink in for a moment. 80% of RAG failures actually trace back to ingestion and chunking, entirely unrelated to the AI model itself. It turns out, spending weeks agonizing over prompt tuning won't help you at all if your retrieval system is quietly handing the AI a broken half sentence. You literally have to fix your data chunking first. And here's how you do it. First, your chunking strategy matters way more than your chunk size. We need to stop using fixed-size splits that arbitrarily slice tables, nested headers, and code blocks in half. Semantic or LLM-based chunking absolutely pays off for technical documents. And I have to highlight the parent doc pattern. It's a total game changer. This is where you retrieve small, precise chunks to ensure a match, but then you dynamically swap in the larger parent block before sending it to the LLM. It preserves the surrounding context and consistently lifts answer quality without any retraining. Let's keep this rapid-fire value going. Your K for the re-ranker should usually be 3. Every chunk past that just adds token cost and latency. Honestly, if K equals 8 is still beating K equals 3 for you, consider it a massive red flag for your re-ranker. Next up, use hide, or hypothetical document embeddings, for free query expansion precision. You basically generate a fake answer to the prompt, embed that, and search using it. It brilliantly bridges the phrasing gap between short questions and long documents. Also, keep your context budget under 8K tokens, and make sure you're using strict continuous integration gates for faithfulness to catch regressions before users ever see them. Oh, and you must version everything. Your prompts, your chunking rules, your embedding models, your re-rankers, the whole shebang. Any silent drift in these underlying components will completely wreck your answer quality over time. You've got to treat your retrieval pipeline with the exact same rigor you apply to your core application code. No shortcuts. Just to briefly tease the absolute frontier of search right now, three-way retrieval is the new high watermark. Combining BM25, dense vectors, and a learned sparse model like Splade consistently outperforms standard two-way hybrid models on 2026 benchmarks. It completely crushes it on complex queries that mix highly specific proper nouns with broad semantics. If your infrastructure can support Splade indexes, absolutely ship it. And all of this brilliantly illustrates why building this specific hybrid pipeline is so worth the effort. Proper retrieval design reduces hallucinations by 70 to 90%, according to industry measurements. 90%. It turns out that when you actually hand an AI the correct, precise context, it magically stops making things up. This solves the biggest headache in artificial intelligence right now, purely through superior architecture. I'll leave you with this summarizing thought straight from our source material today. Most RAG performance gains come from better retrieval, not model fine-tuning. It completely proves that chasing the newest, shiniest LLM isn't the real answer to building a great application. So ask yourself, are you wasting cycles trying to teach a massive AI model when the real culprit all along is just a brittle search bar? Thanks for joining me for this explainer. I'll see you next time.